Hi folks, I'm Austin. I'm a PhD student at Georgia Tech, and I'm grateful for y'all's time and grateful to be here to talk about a compiler we developed for a quantum programming language that we made. So I'm not really here to be a quantum computing salesman or something like that, but I do hope, and I think other people also hope, that someday we'll have quantum computers that are error tolerant enough and big enough that we could use them as accelerators for very specific tasks and get possibly exponential speed up. So, however, despite these lofty goals, current quantum programming languages today are, in my opinion, a pretty low level of abstraction because they require you to think about circuits like this one. So, I don't know about y'all, but to me that's pretty convoluted looking. It's not really clear what it's supposed to be doing. But it turns out, oh, okay, that's a search algorithm, apparently. And I want to hone in on this particular part here that I've circled and show you how you write that piece of the circuit in mainstream popular quantum programming languages today. So as of the year 2000, you might write something like this in QCL. It's the first quantum programming language that I know of. And then in a programming language with commercial backing and support today, you might write something like this. And in my opinion, it's pretty similar, okay? And I'd say that because as a programmer, when I'm writing this code, it's my responsibility to synthesize circuits. Circuit synthesis is on me as a programmer. It's not something that's handled by the compiler. So I want to compare the same functionality that this is doing to how you do it in Qwerty. And you just write this expression. That's it. And so we call this a basis translation in honor of the Unix tr command, because it's really replacing that whatever's on the left there with the thing on the right. So it's replacing these four p states, these four plus states, with the same thing but with a minus sign in front. So here's the overall code for the whole search algorithm. And I'm not going to walk through every line here, but I do want to point out a couple more interesting parts of it. First of all, it's common in quantum algorithms to want to run classical code on qubits. So in this search algorithm, for example, that classical code is a black box oracle that's saying yes or no for a given candidate input. So in this case, this example oracle is saying yes if all the input bits are 1, so just ANDing all the input bits together. And it's really convenient to be able to write this kind of classical code as a classical code instead of needing to scratch your head and figure out how to write it as a quantum circuit like you would in typical mainstream languages. So it's nice that our compiler will synthesize this to a quantum circuit, this oracle up top. Other thing to mention is that in typical mainstream quantum programming languages, it's your job to initialize states. You just get 0 qubits and you have to figure out how to get them into the desired state. Whereas here in our language Qwerty, you just write a qubit literal and the compiler figures out how to synthesize it for you. Okay, enough about the language though, onto the compiler. First of all, why write the compiler at all? Well, the reasoning is that there's been all this effort on quantum compilation already, but that work almost universally expects a quantum circuit as input, not Qwerty code. So it's our job as the Qwerty compiler authors to take Qwerty code as input and then produce circuits that you could pass, quantum circuits that you could pass to existing circuit optimizers, and then ultimately take that optimized circuit and hopefully pass it to a quantum backend where you can run it today on crappy hardware, or my grandson can run it on usable hardware. So I want to zoom in on the Qwerty compiler part of this, because that's what this talks about. And here's the software architecture for the Qwerty compiler. So you'll note we start off here on the left with a Python AST, and that's because this is not a language that we're just doing Python operator overloading or something. No, we actually parse the Python AST, and then we extract from that a Qwerty AST, which is, in our implementation, a Rust data structure, which then we do type checking on it, we do macro expansion, type inference, blah, blah, blah. But this is not the AST developer meeting, it's the LLVM developer meeting. So I'm going to focus on these two MLIR dialects here that we lower to. So the first one is this Qwerty MLIR dialect, and this is an MLIR dialect that we produce from the AST, and this mirrors Qwerty semantics. And I think it's pretty fair to argue this is the MLIR dialect, the quantum MLIR dialect with the highest level of abstraction. And I say that because our operations here in the dialect are defined in terms of bases, instead of you writing a low-level operation like a not, or like a C-not or a Hadamard or something like that. So in general, this Qwerty dialect has two kinds of ops in it. The first are these kinds I just mentioned, where it's these are quantum ops with a basis attribute of some kind, like this state change, this basis translation, state evolution, or a measurement in terms of some basis. But the second category is function-related ops. So it kind of looks like the func dialect a little bit, in that you have like a func constant, call indirect, you have a call, func op, etc. But wait a minute, why not just use the func dialect? Okay, because there's a twist. So in Qwerty, as with honestly many other quantum programming languages, you can call functions in different ways. So for f here, for example, first of all, I could call it forward. So that is, I'm saying running it from top to bottom. But I could also call it backward. So I could call a version of that function that runs in reverse, basically. Or even a little more crazy, is I could take the function, I could run it in some proper subspace of the overall state space. And we call this being predicated. It's a generalization of this idea of controls in typical quantum programming languages. We say predicate because this pattern here is like a predicate describing that the function should run on that middle qubit where the underscore is. But there's even more trickiness to this, because really, when I'm writing f in all these examples, that's really a function value, not just a symbol name. And so it's possible to compose these crazy things and write something like this, where I'm predicating a function, and then I'm taking the inverse of it and then running that. This is pretty spicy. So how do we deal with this in the compiler? I want to show a brief example here. So let's suppose we're starting off with this code as an AST, where it's saying basically call the reverse version of this function f. We would then lower that from the AST to the Qwerty dialect, and you get some IR like this. And the func constant call indirect, pretty much like the func dialect here. But the wild card here, the weird thing, is this func rev op, which is taking a function value as input and yielding a function value that's actually the reverse version. But the thing is, like, what the heck, man? Why are we doing call indirect on a constant almost? It's a little strange. So then we run the canonicalizer, and then we end up with just a direct call instruction. And the thing is, then this has this reversed attribute set to true to indicate that it's a reverse call. So then we just run the MLIR inliner, and oh, wait a minute. How the heck do you inline a function backwards? Okay, so in the Qwerty dialect, it's assumed, and this is the same in the Qwerty language itself, it's assumed that every function that you can call backwards contains only one basic block, at least for now. So then really this problem of inlining this reverse call reduces to how do you reverse a basic block. And so we do this by starting from the terminator of the basic block, and then working backwards, upward through the DAG from the terminator operands. And then, as seen on the right here, then rebuilding the reverse version from top down. And the novelty about this, in our case, is that instead of hard-coding this process for particular ops, the different ops implement this reversible op interface. And so each op just has a build reversed method so each op knows how to build an inverse version of itself, basically. So predication is similar in the sense that we have, if you want to inline a predicated call or call to a predicated version of a function, then we also work backwards up from the terminator, up to the basic block, and then we're using this predicatable op interface for each of these ops. And so in a lot of cases like this one here, we're just modifying the bases of all these basis-oriented ops here. So we're just prepending these ones in this case to run in the subspace where only the first 3 bits or qubits are ones. Okay, so if all has gone well, then the inliner has worked, and so then our code is beginning with qubit allocation and ending with measurement, and it's just a straight line of quantum operations in between, which is a good thing because a lot of quantum hardware does not even have a branch instruction may not even have a stack or a call instruction, despite Qwerty being a functional language. So anyway, ideally it's this case where it's just straight line code, pretty much. But still, in between qubit allocation and measurement there, it's all Qwerty semantics, it's not circuits yet. So the next step here, this compilation process, is then doing a dialect conversion from this Qwerty dialect to this quantum circuit dialect. And this quantum circuit dialect we defined, it's not much to write home about, to be honest. It does the job. Here's an example of one of our ops in that dialect. If this is familiar to you, it's a Z gate with 2 controls, for example. But we took inspiration from some prior work in designing this. The first is McCaskey and Wynn here designed the first, to my knowledge, first quantum MLIR dialect. And so I looked at their code and peeked around a little bit. And then these Cairo and QSSA papers are really nice because they propose this design for quantum IRs where the qubits flow through the different quantum operations, just like SSA normally works. So the qubit dependencies between ops are explicit in the IR, which is really nice. If you want to, you can replace this with one of these commercial dialects if you're into that kind of thing. Okay, so now I'm going to talk about how we go from our core basis translation primitive to a circuit. So the overall structure of one of these circuits we synthesize looks like this. So ultimately, at the heart of one of our primitives here, when we synthesize it as a circuit, the heart of it is this reversible permutation of classical bit strings. And then just kind of layers of stuff on the outside of that, including this vector phase business, which is basically kind of like introducing and removing minus signs, sort of. And then the standardized and destandardized is like removing and reintroducing superposition on the outside there. So I want to walk through how we synthesize the circuitry for this same little bit of kind of quantum chunk of code that I was showing earlier in the talk for that search algorithm. So here, this basis translation op here takes a 2-qubit register as input, and then its result is a 2-qubit register. So we begin here the synthesis process by first unpacking that 2-qubit register into 2 1-qubit values. Then we take the state out of superposition. Then we impart this minus sign, which is this phase of pi, and then we go back into superposition again, and that's the process. So this whole thing, in MLIR terms, this whole thing I'm showing on the slide here is done in a dialect conversion pattern. So it's done without any knowledge of context or anything like that. It's just people. Oh, and at the beginning when we pack, of course, we pack the 2 qubits back into the 2-qubit register so we can replace this basis translation in place. Okay, but that's not the only kind of circuit synthesis that we do, quantum circuit synthesis that we do. Because if you recall earlier in the talk, I showed that you could write some classical code and we would synthesize a quantum circuit from it. And I can tell you how that works too. So that classical function would start off as an AST, and then we would lower that to a classical circuit dialect, the C-circ dialect. And we do some optimizations, some classical digital logic optimizations on it, because this is like a bitwise dialect, pretty much this is. And then from that, then we synthesize a quantum circuit. And that process is basically a reimplementation of this Tweedledum library from EPFL, which is a very nice tool, but it's not maintained, but it's still a very nice tool. Okay, so now the question is though, okay, how good of a job is this synthesis we're doing really compared to writing circuits by hand? So what I got here is I've got 4 textbook quantum algorithms implemented in Qwerty as well as 3 common circuit-oriented languages. And then I've run those to the respective compilers for different numbers of qubits. So the x-axis here is the number of qubits. And then I take all the resulting circuits and I feed them into a resource estimator that's guessing the performance, the runtime of this on a prospective design for a future fault-tolerant machine. So we're in the blue, on the left there, lower is better. And you can see that we're competitive with these circuit-oriented approaches for programming. The takeaway is just that this compiler makes this abstraction competitive with handwriting quantum circuits for these kind of textbook algorithms. So in this talk, I presented some basis-oriented tricks for compiling a basis-oriented quantum language. And if you're interested in more details, then the first QR code is a paper about the language itself, Middle QR code is a paper about the compiler, and then the right QR code is a link to the source code. And I want to thank all these folks at the bottom here, especially Dr. Sharjeel Khan, who's here today. So, thank you.
Fantastic, thank you so much. We've got a few minutes for questions, so start with Mitch.
Hi, great talk. So, when we're talking about the invertible functions, what about operations that aren't themselves invertible? What do you do about those?
Okay. So what we do is it's not a very exciting answer, I'm going to be honest. What we do is in the like up at the AST level, we do type checking. Then we require, so basically, I didn't mention this, but there's two function types in Qwerty. One is reversible and one's irreversible. So if when you define a function, you mark it as reversible or irreversible. And so if you mark something as reversible, then everything you put in there, like all your function calls have to be reversible functions. You can't, at least presently, do classical branching or anything like that. Yeah. Maybe you could do something like Janus. If y'all ever heard of Janus, they're reversible classical programming languages with if statements. It'd be cool to do that someday.
Any other questions? Any more? Last call for questions. All right, fantastic. Let's give Austin a round of applause.